tell two kinds of stories, and I hope that they're connected in some way. I also hope this works. It was working a minute ago. This meeting is being recorded. Everyone got that? Okay, so it won't go when that pops up.
Are you sharing the screen?
Yes, I'm sharing the screen. Yes, I'm sharing the screen. So here, that's my screen there.
Okay.
Very good. All right. So I want to tell two stories, and what I hope connects them is the history dependence or the protocol dependence on how we make packings. So we'll be thinking about packings and how you make them, and you're going to see how much the process of making them plays a role in which ones you get and things like that. So that's sort of the idea. And this is just one example of many examples where this happens in nature or in industry. Here, this is a riverbed, and depending on exactly the flow of water as it deposits grains and they jam, you get very different patterns, and this evolves over time. And you'll see very different patterns if you come back in 10 years or 50 years or 100 years or 1,000 years. You'll see very different patterns here, and that all depends on the way the grains were laid down as we go along. So I want to first start with a very simple way to jam things, to make jammed packings in the real world in 2D. So here we have a bunch of discs. These are cylinders that are very thin in this direction. They're about 3 millimeters thick. They might be photoelastic or they might be stainless steel, depending on what we do. We have other different things, but it's a very thin container, and we shake it up and down like this. And we have sort of two modes of shaking. One, we shake at a low frequency with a very high amplitude, and that really bounces everything up and sort of randomizes the system to get it started. And then we have a very high frequency shaking with a very low amplitude. And at that point, that's just barely shaking them, but it does something very important, which we'll see in a minute. So here's a movie of this going on. These are photoelastic particles. The little white blips that you see are the stress in the material. So photoelastic material can demonstrate its stress if you put it in between cross polarizers, and that's what we're seeing here. So we shake it up and down really hard, and then it starts like this. And this system is jammed using friction. When I say jammed using friction, I mean that the network that makes up this jammed packing actually needs tangential forces in order to be stable. So if you just count up the number of contacts you had here, originally there wouldn't be enough for it to be rigid if you didn't have tangential forces between the networks. We have a network, but normally we think about the normal forces, but here we have to think a lot about these tangential forces as well. And so this thing will not be stable without those tangential forces. But then it's going to run again. We're going to do this. Here's our frictional state here, but now we turn on this low amplitude but high frequency shaking. And as we do that, each time it shakes up and down, it's well above G. Even though it's a small amplitude, they lose contact. Every time they lose contact, they have to fall back in place and grab again their friction. So each time they lose a little bit of the frictional tangential force, and they fall down into a state which is now rigid without tangential forces. So this is a standard jammed packing. Okay, so that's what happens. And one of the things that you notice right away is that when you do this over and over and over again, and we did this 500,000 times, you get this packing 5% of the time. So 5% of the time you get this packing or the flipped version. So I'm not gonna worry about the flipping of these. I'll consider them the same packing for this. So you get this 5% of the time. The next most popular is this one, which you get 1% of the time. This guy we only got once. Okay, in the simulation they actually got it twice, but I think they did 10 billion or some crazy number. I couldn't wait 10 billion times. So to sort of track these systems, it's hard to look at the whole phase space. We'd like to look at the whole phase space, but there's 7 particles here in 2 dimensions, so that's a 14-dimensional space. So that's very hard to look at. So what we're going to do is we're going to look at a projection, and one of the projections we'll look at is just the centroid of this. We just take all the distances and average them, and we get a center position of this. This is all the centroids of all the states that the experiment found. So here's every single state that the experiment found. We also did this same exact experiment, same sort of thing with gravity. We throw it up and so forth, let it fall under gravity in a simulation. And here are all the states that the simulation got. So you notice there are a few states that the experiment got that the simulation didn't, but overall there's a 95% overlap. So mostly if we found it in the experiment, we found it in the simulation. They found more states in the simulation than we did in the experiment by about 30. Those are harder to find. They're in this region in here. These states that the experiment finds that the simulation doesn't is because of the protocol that the experiment does, the simulation does. The simulation lets them fall in a way that's not quite as conducive to these high center of mass states. And so they can't get them that way. If we worked on it a bit, we might could get them, but that's as good as we felt we needed. Now, to just sort of see how good or how good the simulation is and what these states are like, let's zoom in on this little tiny box here and see a certain area. So here's this area here. You still see the simulation and the experiment are matching up very nicely. Let's zoom in further. So here's times 750. Now you can see there is a little bit of difference between the simulation and the experiment, but they're still quite well separated. We can definitely tell that this guy goes with this guy goes with this guy, just from the centroid. Of course, we can also tell from the packing itself, yes. You're about to see. So we take this to 750, we take this to 6,000, now you can see the individual points that make up the experiment. So they're still way separated from this. We can really tell which state this is. And that's one of the key features that we found in this, is that experimentally, even though we knew this in a simulation case, experimentally we can also show that the states are distinct. So you get certain particular states, and those states are separated by quite a distance. So if we look at this first peak, this is the distance in both the simulation and the experiment between unique states. And that's up around a particle diameter. This is a distance in phase space, so this is a distance in high dimensional space, but we normalize it by the particle diameter. So 1 on here is 1 particle diameter away in this high dimensional space. And so most of it is here below, above say 10% of a particle diameter. Then these two guys are where we find the error in the experiment and the simulation. So that was that little cloud of points that you saw on the one thing there. In the simulation, we can just we can move this back as far as we want. We just keep simulating, getting better and better and better and better and better. We go to quad precision, we could do more. We go to infinite precision, we can go more and more and more. We could just move this as far as we want. In the experiment, we're sort of stuck here. But what you can see is there's a very clear gap between what we think is one state and what we think is some other state. And so these states are unique, and this gap doesn't seem to go away as you go to bigger and bigger systems. So you have a bigger and bigger system, there's still going to be a gap. You can kind of understand why. There's kind of no way to find another state that's just right by another one. It's really hard to find those. There might be a few, as you get larger and larger, there might be a few that are very close together, but you kind of think to get to another state, you have to move something, you have to flip something somewhere, you have to move something a finite distance in order to find that new state. And that's what we find experimentally and in the simulation. So in the case where there's rattlers, then you can decide whether you want to consider those very close states. What we usually do is think of them as one state with the rattler taking up an area. And so there's a fixed area that the rattler can be in, and as long as it's in that area, we consider it the same state. So between those there are. And in the landscape, if you're thinking about a density landscape or an energy landscape, those are places where the jam state is not a point, but it's a little flat. There's a little flat spot wherever that is. And so that's another way to think about it. Also, the other big thing that you see is that, as I mentioned, these states have highly different probabilities. So here is the probability. We've sorted these by probability. Here's the probability of getting the most probable state all the way down to the least probable state. And in the experiment, there's 5 orders of magnitude in this. In the simulation, there's 8 orders of magnitude. And that persists. If you go longer and longer and longer, you just move that out. Now, in a case like this, we might have, with only 7 particles, we might have completely saturated this. So this might be the end of it. Not in the experiment, but in the simulation. That might be all the states there are, in which case this will stop. But if you go to a larger system, of course, this just continues on. And so this is very different from what you get, say, if this was a fluid. In a fluid, all the states are equally probable. And so you're able to do a lot of things with thermodynamics, and you can understand these systems by saying, well, if I want to pick a random state, what's it going to look like? Well, I just take all the states and I just pick one, and that's what the random state will look like. You just can't do that here. And so this kind of system is not amenable to that kind of analysis. Okay, so just to reiterate what we learned from frictionless systems is that the experimental packings are distinct, and they have the unique states are not equal to probability. There's a huge difference in the probability. These other things are, other interesting stuff about the experiment. So just to reiterate this, the states are not equally probable. States are zero-dimensional points. So this is a very key part of understanding why we can't just think of this in a normal thermodynamic way. That's because each state is a point in the phase space. There's no way to think about density in the phase space, because if you start making the circle bigger, you're just including states that aren't necessarily related. There's no small region around every state where you can say, well, everything in this region behaves the same, because the only thing in that region is that one state, and there's nothing in those other states. So that's a key problem in this concept of phase space volumes. And of course, there are no frictionless particles in the real world. So if we really want to understand the real world, we also have to understand friction. Okay, so now I want to talk about the system again, same system, but now I want to focus on the frictional part, the part before we packed it down. And so here is one of the initial states that we can have, and here is the centroid of that state. The red dot here is the centroid of this particular state. Now, when we were looking for frictionless states, we just turned on this defrictioning shaking a lot. We just turned it on for 1 second and waited. Turn it on 1 second, wait, turn it on 1 second, wait. But what we can do instead is just turn it on for a half a millisecond. You turn it on for half a millisecond, then it'll just lose friction a little bit, and then it'll stop. And it'll lose friction a little bit, and you stop. And we call these taps. So we're going to tap it once, we'll lose a little friction. We tap it again, we'll lose a little friction. So here's no taps. This is where it started. We tap it once, it drops. This is a stable state, another new stable state. We wait long enough to make sure that these states are stable. So this is a brand new state that's stable. It's not one of the states that you can get in the frictionless case, but it's a new stable state in the frictional case. And you see the center of the centroid dropped when I did that. Now I go again, it drops again. I go again, I go again, I go again. It's dropping, 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 dropping. Now here, when we get to here, we get to 10 taps, this is the bottom state. Now it adjusts itself a little bit on 11, but then 20, it's still the exact same state. So eventually it gets to a point and it stops, and that's the final state at the bottom. So this is a frictionless state, and this is a frictional family, or what we call a frictional family. So these go along this line. Now you might wonder, well, is this, just, probabilistic? Will we go a different line if we do this again? What happens? Are these lines robust? And so here are all the lines going to this state. And if you look carefully, you can see there's the blue curve, but when you put it on top, there's a pink curve that goes on there. There's a red curve at the bottom that follows it. There's a black curve that goes there. So that same trajectory was covered by many, many times as we go along. And there's a bunch of these trajectories, and they appear to be some kind of one-dimensional structures. So the jammed states were, the frictionless jammed states were points in phase space. These appear to be something like lines, something like one-dimensional structures. So to sort of, here's a big version of that. So you can see all the different lines that come in. And many of them are repeated multiple times. Okay, so to sort of take this home, let's think about the number of contacts. In this context, we can count the contacts to determine if it's rigid. So it's all we have to do, some kind of Maxwell counting to do that. So if we start out with 12 contacts. We have 7 particles. We will need 14 in order for this to be stable and rigid. So we have 12 at this point. As we tap it, what happens is it stays 12, but it's a different 12. So if you watch this guy, it flips from here to there. So that's going from 12 to 12. So that's one state that it goes down. As we go down, it adds 1. So now 1 more contact is going to get added right here. Whoops, 1 go forward, then 1 gets added. Now it stays 13 for quite a while. So here it's all the same state, the same part. Now we switched to a new 13, we go back to 12 momentarily, then we go back to 13, then we get to 14. That's the final state that we get to, all the way up to 20. Now, one way to think about this is in terms of 14, but a better way, or a way we like to think about this, is instead of thinking about the total number of contacts, we want to think about the number of contacts that you're missing. to make the state that's stable, frictionless. And so since we need 14 contacts in order for this to be isostatic, for this to be stable without tangential forces, then we can write down the excess, the missing contacts, basically. So no missing contacts here, one missing contact here, two missing contacts here, one, one, two, two, and so forth. This, yes?
Is that coordinated to the diameter of the disk?
No, not at all.
Isn't a contact on the
This one is not a contact, no. It just is close, yeah, it's just close. Yeah, they don't fit exactly across. Yeah, it's if you had a better resolution, it's close. Yeah, it's not that far off.
That might have something to do with which states are getting raw.
It could definitely. The shape of this could depend.
I would think that it would like either one big one.
Yeah, that is a common situation. And the lower the center of mass is, the more common it is as well. There's several commonalities, but none of them are ironclad. And in fact, we actually did, I won't talk about it today, but we actually did this experiment where we changed the size here from all the way from one particle going vertically, so it was just a chain this way, to all the way out this way. So we did look at this entire thing. And in that case, even though you do see this fairly regularly, you don't see it in other places where you might expect it. Like when you get to this size with three down here, the chance of getting 3 is very low. You almost always have a big one in the bottom. So, you know, these things are part of it, but they're not determinative in what goes on. Okay, yeah, sure.
So when it goes from one 12 to a different 12,
Yes.
it breaks a contact and forms a different
Yes.
contact. So then it goes to a 2-dimensional.
Good question. I should have my plant in the audience. So what we can think of is when it's 0 here, we have a point in phase space. When it's 1, we have a line, a one-dimensional line. When it's 2, we have some kind of surface that lives in the phase space. And when it switches from 12 to 12 up here, it switches from one surface is connected to some other surface that it switches to. So it moves up this surface, and then it finds a new surface and falls down. That surface, up and down are not really relevant, but my hands were that way. So this is the key observation that explains a lot of what's going on in these systems, and also the observation that will allow us to do some kind of statistical mechanics on this. Because now we have real volumes. We can talk about, for example, on this surface, what is the probability for getting a certain part of the state on the surface? Yes? No. These are, well, because these are all stable states. So unless the 11th state was also stable, you wouldn't see it. It probably will move through 11. It might move, there might be other things that jiggle or something as it goes along. But if that 11 was stable, we would have seen it. So it would have stuck there, then we would have seen it. But an 11, in that transition part, that one didn't have enough friction or whatever it was to not make it stable. So it moved on to the 12th state. I believe in this system, you can't have 11 stable. I don't think there's enough, even with tangentials. I don't think you can have, I don't remember. We'd have to check that. But yeah, and when you go from a 1 to 1, you also would see a 12. It could be there, but we just didn't see it. It's not. So when we vibrate it, it's moving, but then we wait for it to stop moving.
Yeah, no, that part I get. So like the in-between state when it's moving, it's like you have 0 contact.
It's like we have 0 contacts in that sense. We definitely have 0 tangential contacts. We still maintain pretty much the normal contact because the vibration is so low. So yes, we do get rid of, you can think of the contact is sort of still being there, but the tangential portion is being lost. Just the steric consideration keeps the normal part in play. Okay, so our picture is that in the real space, in the real phase space of the positions of the particles, so this is a 14-dimensional space or 2n-dimensional space or d-n-dimensional space, you know, in general, that in this space, jammed configurations that have no tangential forces are points. Now there's the issue of rattlers, and we can think about that, and that's something that I'll talk about in a minute. But then if you have, the next possibility is that you have a line, the next possibility is you have a surface. So in this space, as we lose context, we're increasing the dimension of the object that is determining what's going on. Now, there's another space to think about in these problems, and that is if we write down all the forces, so the normal forces and the tangential forces as a vector, as a column vector, then there's a matrix C that we multiply times that total vector that has to be 0 for it to be in force balance. Okay, this matrix C, if you have no tangential forces, has a very big null space. Okay, so when we're down here, you can imagine if we don't need any tangential forces, we can stabilize it with a huge amount of tangential forces. There's almost any linear combination of all the tangential forces will allow it to be stabilized because it's already stable. So adding those on doesn't add a lot to that. But as we climb this, as we add this line that has to live on this line, now the null space here is shrinking. Null space is getting smaller and smaller and smaller. Eventually, we will get to a point where the null space no longer exists. There's no null space. At that point, you need every single tangential force in order to solve it. And it becomes a point in the force space. So we start out as a point in real space. We move up in dimension this way. We start out as a high dimensional space on the force space side, and we move to a point. So there's only one force at the very lowest value. And that value comes when there's 3 contacts per particle. So when there's 3 contacts per particle, the only way to stabilize it is use all of the normal and all the tangential forces. And there's only one solution. There's only one solution. Now on top of this dimensional hierarchy that we have, there's another consideration, and that is friction actually depends on a number, a material number, and that's how good the friction is, how strong the friction is. So when the friction is strong, you can increase your tangential force to a large fraction of your normal force. So normally the friction coefficient is the maximum tangential force you can get for a given normal force. And this number determines how strong these are. And so you could have no friction. That's the case when we go at the bottom. But you could have very large friction. You can even have infinite friction. You can imagine infinite friction where if these particles were like gears. So if these were like gears, then pretty much almost any normal force I can make will give as much tangential force as I want. So we can imagine this going, and that's what these contours are supposed to represent. In this space, if I had infinite friction, I could stabilize any of these structures. But since I have finite friction, as I change the friction, I'll change the amount of stuff that I can actually, where states actually can exist. And sort of our basic idea is that the probability of these things is some kind of product between the real space and the force space. That thing has a constant dimension, and that thing is where we can do statistical mechanics because everything in that space lives in a specific dimension. Okay. So let's test this out. Okay, so we're going to test this out in a simulation. This is a periodic box with 6 particles in it. These are all the possible states. We ran this to completion. There's no more states than this. There are there's one state that's that has a floater, and so we'll treat that one differently. It would have to be treated differently. But the rest of these states all have the 11 contacts that are needed for a periodic. In general, with this type of Maxwell counting, all we're saying is that the total number of constraints, which is the number of constraints per contact, is equal to the total number of degrees of freedom minus the boundary condition. Depending on your boundary condition, you can move up and down, or you could rotate, or different things like that. In the case of periodic boundary conditions, this is just the dimension of the system that you can only move up and down. You can't rotate in a periodic domain. And then you have 1, because what we're imagining is we're jamming these. So we also have to grow them. So the diameter of the particle is a degree of freedom. You could just think of that as being in the degrees of freedom, but we usually break it out because it depends on the way we jam it and things like that. So that's another thing. So if you do this calculation for In the case of 6 particles in periodic dimensions, you get that the number of contacts you need is 11. Okay, so let's take that system and try to identify all of these points, all the points. Now, we could use the centroid again, but in periodic boundary conditions, the centroid is not very well defined because it's one of the symmetries says you can put the centroid anywhere you want. So we have to use something else. So what we used, you could use pretty much anything, it doesn't really matter, but what we used was the distance matrix. So we just take a matrix made up of the distances between every particle, and we take that matrix and we look at the invariance of that matrix. Now, the first invariant, the trace, is 0 for this matrix because the distance matrix has all zeros along the diagonal. But the second invariant is perfectly fine. You could use the third one. It really doesn't matter. Like pretty much anything. You could just project it. There's all kinds of things you could do. We just picked this so we would have something concrete to use. So in this space now of Q and packing fraction is another good parameter in periodic boundary conditions because it doesn't depend on the position. So these are just 2 numbers to compress this 11-dimensional space down to 2 dimensions that we can look at. So these are all the points that you can find. And again, these guys have hugely different probabilities. Okay, we don't know what the probabilities are. But now, let's now see if we can find any of these first order states. So now in the simulation, we turn on friction and we try this again. We just, in our simulation, we add static friction. This is easy to add, and we see if we can find these. So here's what happens if you turn on friction. You turn on friction, all the red points were those original points, the point sources that we got. But all these pink points, all the green points, all the blue triangles, those are all new states we found when friction is turned on. New states that happen to be m equals 1, this place where they're one-dimensional states. And furthermore, we see something else interesting. The blue triangles have the lowest friction, the green, whatever they are, have the next highest friction, and the pink have the largest friction. So what you see is these families, these lines, depend on the friction. More friction you have, the longer the lines are. And so this is going to become important. What we can basically see is the length of these lines depends on the friction coefficient in not necessarily linear, but we'll see it is linear, but at least it depends on it. It's proportional to it. Okay. So now we want to try to generate all of these lines. So when you just jam it at random, it's going to take forever. These are lines. So there's an infinite number of them on every line. So if there's a line that happens to be very probable, you're just going to find all these things on this one line. You're never going to get to other lines that are less probable. So can we come up with a way of generating these states on their own? So we take our packing, here's one of the packings, and we pick out one contact. So this is one contact, the contact between particle 1 and particle 2. What we do is we stretch that contact, okay? Now if we left these particles as regular particles that, I get my terminology wrong, but you know, the one where you push on it but you can't pull on it, bar, I don't remember, is that the bar? I don't know, rod, I don't remember. Strut, okay, so the strut, thank you. So these are struts originally, but we turn them into springs, which I guess is the, you know, something, it's both ways, it can pull both ways. So we turn them all into springs. Now, when we break this one contact, we have that 1 degree of freedom that we need. This spring network is for sure stable and rigid whenever, with this number of contacts, but we break one contact, now there's a way to go. We can move, there's one direction that we can move. And so we just keep pushing that. We push and push and push and push. What will eventually happen is 2 particles will run into each other and a new contact will be formed, and now we'll be in a state that's rigid again and we can't go any farther. Okay, so if we do that, here are the original pink states that we found from the thing. Here are all these blue ones. There's 11 of these because there's 11 contacts, because that's the number you need to make this state. So there's 11 of these lines, and these are, so many of these we never found. We never found this huge long one. So very huge and long, but we never find it just randomly by going, probably because something on here, you know, depends on the shapes or other things that, you know, make it go that way. Some of these other pink ones that we don't find, these turn out to be parts of other, you know, parts of other points. So like this set is actually connected to that black point there and that black point there. So, but we find all the places where we had pink. If we do this for all the original states, we find all the pink points. They all come up when we do it this way, plus a whole bunch more that we couldn't find otherwise. Okay, so if we can find the one-dimensional structures, can we find the two-dimensional structures? So we just do our same trick again. We do our same trick by first moving a little bit in this direction. Then we pick some other spring and we push it apart. So we move this one a tiny bit, then we move this one back and forth, and then we move this one a tiny bit, and then we move this one back and forth. So we scan over a two-dimensional structure. And so now we can find these second order surfaces. And here is one of those second order surfaces. So here are the two springs that we individually move. This spring will fall along this line. If we individually move the other spring, we'll fall along this line. And when we move them simultaneously, we'll move out and follow this surface. So this shows that this basic idea that there are structures, one-dimensional, two-dimensional, three-dimensional, four-dimensional, five-dimensional, and so forth. As we move contacts, this works out, and you can actually stabilize these things. And you might wonder whether you can get these states, these two-dimensional states, by just compressing, just by finding. And that's what all these triangles are. These all live on this structure, and those were ones we found just by compressing. Okay, so now what we want to do is try to apply some kind of thermodynamic-like argument. So we want to try to really understand what we're going to think of as a configurational entropy. So what we're going to say is that the partition function for this is proportional to the volume in real space of the structure that we have, but that volume is modulated by mu. So it depends on mu. So it's this structure plus the fact that there might be a mu dependence on the structure. And to just check that out, here we've actually calculated this. So we actually calculate the mu structure. So here's one of these planes, and here is log mu, and this is where you would get each one of these. So as we go out larger and larger mu, as we go smaller and smaller mu, this gets longer and longer. This is log 0, so this is large, and so this depends. So this depends on mu. The probability of getting it depends on mu. Okay, so how do we actually do this in math? Because how do you compare a point to a line to a plane? Well, you can't compare a point to a line to a plane. The area, is always bigger than the point and always bigger than the line. So what we do is we sort of say that phase space is going to be broken up into little balls that sit around the points. So we have a little ball that sits around the point. We're just going to give it some very small number, and we're going to assume that in the end it won't depend on this very small number that we pick. And so what we're thinking is that we take this line and we extend it by delta in all the other directions. So this is a high dimensional cylinder. This cylinder has a dimension of 2n minus 1, which is the total number of dimensions in the space, minus 1 for the fact that it's a line. So this is a high dimensional cylinder. This is my poor drawing of a high dimensional cylindrical surface. So it's a surface in this direction, but in these other missing directions, it's a cylinder. So it's just a cylinder. And that guy, that cylinder side has 2n minus 1 minus 2. And so you can see m goes here. So it's m is the number of surfaces. And this works out even for the point, because the point better be just a ball of delta at the point. Okay. So now let's just work it. That was picture. Now let's do it in math. So in math, what we're saying is that the partition function is the volume of these manifolds that depends on m with their mu structure times a little tiny bit that brings it up to the size of the space in dimension. We know that there's a sort of size to. Let me just go back. So what we know from looking at the pictures that there is a sort of size dependence along here. So when mu is 0.1, you get out to here. When mu is 0.2, you get out to here. Mu is 0.3, you get out to here, 4, 5, 6, and so forth. And the same thing happens in the 2D area. So we should expect roughly that this guy should be a length of mu, and this guy should be roughly an area of mu squared. Okay, so that's what comes in here. We say there's some length scale associated with mu that tells us how big the actual thing is. And that gets raised to the m to give you the volume of this structure. And the nice thing is when you then normalize this by z0, which is the thing we don't know what the probability of the points are, this gives us something that just goes like m, some function of mu that just goes like m, and we think mu is proportional, L is proportional to mu, so we think this is just mu to the m. So let's ask, can we write this down as some number times mu to the m? Is this just a polynomial in mu? And so for this data, we can actually calculate this. We try to go beyond 2 dimensions, it just takes too long. So this took about 10 minutes, this took about 4 days, and the next one would take a couple months or a year, I don't know, something in that, longer than the graduate student was willing to go. So, but these are nice lines and a log-log plot, and so when we put the square root here, this becomes a line, and so this tells us that this idea that it can be just expanded in mu is perfectly good. So now we want to find the probabilities. We have the partition function, so what we do is we just take the probabilities, we divide by the total probability, sum them all up, and because we don't know A0, we can divide it out. And this is the key to this. We don't know A0, but we can divide it out because the rest of it doesn't depend on that. And that's how you can get around this big problem that everything lives in a point. Okay, so now we have to figure out what A is. Okay, so we could just measure A but as I mentioned, it takes a really long time to measure A. So let's see if we can figure out what A should be. So what we think A should be, it first should depend on this number of states that are available, so the number of points that are in the phase space. But then it should depend on the number of branches that go out from each one. Well, the number of branches we can basically count. Okay, so we start from a point here. If there are 11 contacts, then there'll be 11 branches that go out of each point. If we're on a branch, now there'll be 10 little planes that can go out. If we're on a plane, then there'll be 9 little volumes that can go out. And so what we get here is just the product of 11 times 12 times 10 times 9 and so forth, this so-called falling factorial. And so this is a common symbol for that falling factorial. So we just expect it's going to be n minus m product up to the m that you're on. And so we can just try that out and see whether that works. Okay, so we try that out and see whether it works. That's up here. Now let's try to explain what's going on here. This is the probability given m, the number of missing contacts, and mu, what is the probability that you'll get that state? So here is the m equals 1 state. Okay, so what it says is when mu is very, very small, then you have 100% of m equals 0 state. So when mu is very small, you only have these states that can be stabilized without tangential forces. So that goes down there. But as you increase mu, the m equal 1 states grow. But eventually the m equal 2 states dominate, and the m equal 3 and so forth, until you get all the way to the other end, where the force space is now a point. When the force space is a point, now there's only one way to go again. And so on this side you get out, and when you get to the highest frictions, you get 1 state again. Your probability has to be in that 1 state. Okay, so this looks right. This is basically what we expect. This is what looks right. The dots down here are measured from the simulation. But as you can see, this doesn't really match up. So the position of this peak doesn't match up. The depth of this little thing doesn't match up. So it doesn't match up quite. It gets all the qualitative features right, but not the quantitative features. Okay, so what can we do? Well, what we did was say, let's imagine that instead of just depending on the branching probabilities, these branching probabilities that we calculated, let's say that there's some other contribution to the branching probabilities that depends on n. So where might this come from? Well, one thing, it could come from the floaters. So as we're going along, we might incorporate a floater. At that point, the system changes its whole big dimension. And so that would change the number of times that we could get things. So we sort of expect that as you sort of go out in this thing, you should expect there's more ways to make these things than you would normally expect. So if you think about that, and there's a couple of other reasons which I won't go into, you should expect that this number should start out small, get big in the middle, and of course it has to go back down to 0 on the other side because, again, there's only one state at the other side. And so we actually measure it. This is what we find. These are the points we actually measure, and it nicely fits an exact Gaussian distribution. And that Gaussian distribution is basically centered at m equals half of the maximum. So in the middle, where you have the sort of most degrees of freedom to play around with, where the force space is big and the real space is big. In that place, it's the biggest. That's where you get more m's than you'd expect. You get more stuff than you'd expect. And out here, it goes back to 0 and back to 0. So when we add this in, that's when you get this, this comparison. So the dashed lines are from the theory. And there is one adjustable parameter, which is the height of this. So we don't know that height. So that's the one adjustable parameter that we got from the simulation. But other than that, everything else is figured out. And so this matches up very, very well. And so this guy is the Z iso line. This guy is the iso -1 contact. Since we're doing Z, then Z is number of contacts divided by the total number of particles. So we do that, and we go out all the way till we get to this point, which is Z iso -1 or 3, since Z iso is 4 for this case. And then that's the one that ends up on that side. So that allows us to really calculate this probability, and it puts this kind of problem back in the hands of statistical mechanics in a place that we know and love. And so we can do a lot of things with this. So one thing we could do, for example, is figure out the contact number as a function of mu. The average contact number is a function of mu. We can get this from this theory now without having to do the simulations. So these solid lines are from the theory. The points are from simulating this. And so this matches up very well. So this is a very good way to be able to answer any question where you're asking what's the probability of getting a certain state when it has friction, when friction is a possibility. Okay, I'm gonna skip this. Yeah, I'll skip this. It works out in the experiment roughly, but we can't go very far. So let me summarize the frictional results. Each frictional state lies on a reduced dimensional manifold in the full configuration space. And that we can make a partition function for each of these families determined by M in our simple theory. And the key feature of this is that the volume depends on mu. So the volume mu determines the volume. This works with all n with only one fitting parameter. We set the fitting parameter on any n, and it works throughout. Predicts distributions that we see. Okay. So now I want to switch gears a little bit and try to tell a similar story about protocol dependence. So the protocol there was friction, changing the friction as we go along. But another way to imagine jamming something is to compress it, but not to jamming, and then shear it. So we're going to compress and then shear. If we compress and then shear, you might think, well, we compressed, it didn't jam. Why could it jam? How could it possibly jam? It does. There's no jamming state there. We've compressed it. There was no jamming state there. But it turns out that that's not the case. So here's a way to think about this problem. So here we have stress on this axis. Here we have density on this axis, and this is what people often call unjammed, and this is what we will call jammed. And what we're going to do is we are going to move at zero stress along this axis. So we're going to compress. So here's a picture of compression. We move until it stops. At this point, it's jammed. Now we can go further in here if we want, and you do typically go a little bit in. No matter what you do, you don't know that you're jammed yet until you've gone a little bit over. So very often we're in this case. And now we could imagine if we were to apply a stress. So if we apply a stress at this point, what will happen is it will move up this. The stress will move up. It'll stay jammed. But at some point, that stress will be too big and it'll break. Something will happen. Two particles will interpenetrate. Something will happen. These are not hard particles. They are soft. So something will happen. If this was hard, you can't move here. So in the hard limit, nothing happens here. Okay. So that's one possibility. Now here's another possibility. Let's go only up to a finite distance below jamming, below the point where we jam. So that's what we did there. Now we're going to shear this. We're going to keep shearing. We're going to keep shearing. We added a contact. We're going to add one more contact. No, there we go. Okay, now it's jammed again. Well, how can this be? This is in the unjammed region. We are now sitting in the unjammed region. How could we possibly be sitting there? These states created by shearing are in the unjammed region. They exist only in this sort of small range that live down here. And further, they have a distinguishing feature. When you look at their stress, it's anisotropic. So it knows what direction you were shearing in before you sheared, when you sheared. So are these states, are these states inaccessible by compression, or what's going on? So let's sort of step back and think about this diagram again. So I don't really like this diagram where we put stress on an axis, because I like these things to be geometrical. Stress is a force. I prefer a strain. So I like to think about, I put a particle somewhere rather than I push on it, because when I push on it, that's dynamics and it's much harder. I can't do all the geometry I like when I have that. So let's try to translate this picture into a stress strain diagram instead of a stress density diagram. And then when we do that, we'll then do it further, completely geometrize it by looking at the stress, the strain phi diagram. So there's sort of three diagrams we can have here. Let's just first orient ourselves to move over to what strain is doing in this same picture. So in this picture, we are straining here. That's at this point. Okay, it's sitting at this point. We're straining. We're sitting only at this point. The green is just a point there. Then when we get to the jammed state, now the stress can take over and move up, and now we'll move in a diagonal, just like any normal stress strain curve. So typically there's linear relation between stress and strain, but this whole thing is, we don't see it. We don't see that green part. We don't notice that we're straining, because at when we first apply the stress, it's free to strain without doing anything. It didn't cost any energy, so it just kept accelerating and then that's one of the issues. Okay, so now let's move to the case where we're going to think about what happens in the density strain space. So this is for a particular case. I think this is 30 particles. This is 16 particles. This is the density and strain plane, and how we make this diagram is we set the system at a particular strain, and then we compress. So we set it at a strain, then we compress. We set it at a different strain, we then compress. So all we're doing is changing the shape of the box before we start. So we start with the square box. That's over here at zero strain. We jam. We look at all the states. So this one line is the entire jamming diagram for the square box. Okay, so we found a state here, we found a state here, we found a state there, we found all these states, okay, as we move up. So as you move up here, at some point you'll run into one of these states. This is a projection, so you don't have to run into the lowest one always. You can run into any one because it's a projection, so you don't know exactly where you started. There's lots of other dimensions. But we can make this entire diagram by changing the shape of the box and doing it again, change the shape of the box, do it again, change the shape of the box and do it again. So that's what's done here. Okay, and what you see in this space is that these families, just like the families for friction, now we have 1 degree of freedom left over. Whenever you jam something with compression, there's always one direction you can go and shear it. So that's a picture like this. So if we were sitting here and we were to go up, and if we go up above here, we'll jam more because we're going inside this state. But if we were to go left, we will unjam. And there's no jam state out here, and we will just become unjammed. So if we try to shear this way, we will have to move a long way because there are no states. We'll have to wait until we get around here, then we can maybe run into this one, or we could run into this one. This is periodic, so we just move back in. So if we go up here and we were to go this way, we would just keep going, and maybe we run into this, or run into this, or maybe we have to wait to run into this, or maybe we have to go around 5 times before we run into this. And so just because we don't know where we are, basically, this is just a projection. So that's the picture here. So when we go up, we run into these. We'll always run into them. There's always a place where you'll run into them. But when you shear, you'll miss them. And this is the key idea, is that if I were to come up here, it looks like there's no way to jam here. And there's not. At that box shape, there is no jamming spot there. But if I'm allowed to explore horizontally, I'll find a jam state. This is just the jam state I'd find if I started here and moved up, but it wouldn't be found from the square box. I can't find it from the square box, from jamming the square box. Okay, so to just sort of test this out very carefully, we think of 2 protocols. So here's a idealized phi strain diagram. So here's a state. Inside here we're jammed, outside here we're unjammed. So we have 2 protocols. One is we jam, we compress, and then we shear, and that brings us to a jam point. This is the so-called shear jamming way of doing things. Another protocol is we first strain, and then we compress, and we get to and the question is, can we get to the same points? What types of points do we get to? Are we always going to have the same points? So these are the 2 protocols. So this one, we first compress, then we shear. This one, we first shear, and then we compress. Okay, so that's the basic difference. And when we do this, we do find that there's a big difference in the states that you get. So the states you get when you use the isotropic compression way. So sorry, when you use the isotropic compression way. So if we start with the box in a certain shape and we jam, we get isotropic stress. This is the probability of getting a particular stress tensor. Sorry, this is the one component of the stress tensor. This is the shear stress. So this is the probability of shear stress. It's equal, plus and minus. Okay, but if we do the shear jamming protocol, we never get negative negative stresses. And of course, this already makes sense to us because we know one way it's not stressed. The other way it is stressed. And so when you run into it, that's the only way it's stressed. If you were to back off, it wouldn't be stressed. So we already sort of understand what's going on here. But we want to sort of really nail this down very carefully. And so what you can do is now think about, here's a real trajectory in the phi gamma plane. If we measure the stresses here, we notice that these guys are roughly parabolas. So phi as a function of strain is roughly a parabola, and the stress as a function of gamma is a line. And you can go through, and if you take this ansatz, that phi is a function of gamma and it's a parabola or parabola-like, or you just take the approximation, then you can plug it into this formula that you can derive in general. So you take this is a general formula you can derive for the stress. Doesn't matter what the function is here, but if you take this, then you expect that there will be a line here. Okay, so the stress will be a line related to this parabola. Okay, so how do we understand what's going on? I've already sort of told you, but I just want to take it in this thing. So in this picture, the stress is positive on this side and negative on this side because of this minus sign. Okay, so when we do isotropic jammings, when we go to a particular strain and we go up, we can get to both sides. We can get to both sides, and so we have a collection of negative stresses and a collection of positive stresses, okay? And so that's why we get a symmetric picture here. On the other hand, if we go up and then over, we will never get to one of these sides. We will not run into these ones. In fact, if you were here, inside here, and you ran this way, you would unjam. You would not jam. You unjam on that side. So you never get this negative side. You always get the positive side, okay? And so it's just the difference between these two that matter. I'm not going to talk about it today, but there's also another difference that comes out in the protocol. If you think about the probability of running into a particular value of this here, the slope changes what the probability is that you'll run into. When I'm running this way, it's very hard to find this bottom. Very hard to find this bottom. There's only one place where I get it. When I'm coming up from the bottom, I'm going to hit it a lot of times. So there is a probability difference built in to the structure of how you go. And this is another way that protocol plays a role in these systems. So just to put the final nail in the coffin, what we can do is we can take this protocol where we go up and over, shear jam, but then once we're at that point, we can just unjam it a little bit and come up and see if we get the same state. If these are truly states that you can't get from compression, you wouldn't be able to come back up and do it. And so here is the distribution of the sigmas that we get from both compressing and shearing. You don't always get back to the exact state, because when you decompress, you might move a particle a little bit. When you recompress, it's going to come out. But most of the time you do, and that's why these two things are not exact, but they have the same distributions regardless of what you do. And you can do the same thing, but with the other protocol, where you first find this and then you shear jam it back and forth, and you get the same distribution as well. Okay, so good timing. So for these systems that jam at p equals 0, shear and compression protocols produce the same set of states. So there's no new states. Shear jamming is not a new thing. Those states were always there. You could have gotten them by just changing the shape of your box and jamming. So those states are not new. But what is new is that the probability of getting them depends on the protocol. And mostly it depends on this fact that we have a parabola, so the slope is changing. So depending on how you approach it, then you get a different probability of having a state to go. For these shear states, these are single-sided. So when you come in and you shear, if you backed off, you would unshear. Whereas when you go in a compressive way, you go inside and you can move both ways a little bit. Okay, so that's a difference that happens. If you're interested in finite pressure, we've written a couple papers. It's actually very interesting what happens when you actually allow finite pressure, what happens when you move inside and see this happening again, because inside every one of those parabolas, there's other parabolas where you add new contacts. So we had our M value, which is when you remove contacts. You could have minus M values in that terminology, where you add another contact and you have more pre-stress, more stress available to you. And then interesting things happen as you go to those, because then those systems are sort of over-determined as opposed to underdetermined. The other interesting things are effects of rearrangements. That is what happens. All this we've been assuming that no matter what we do after it jams, the contact network doesn't change. But what happens if you go too far and the contact network changes? Then you can imagine If I'm on the bottom of one of those parabolas, I come in from the side, I could go out the other side, and something new will happen on the other side. So that's something interesting. If you want to see how that applies to riverbeds, we also have a paper on that. That may be too far astray for this crowd, but anyway, that's there. And I'll just leave you with another packing problem that we've been very interested in lately, and that's the packing of deformable polygons. So how do you think about the degrees of freedom in that problem when the particles themselves have a lot of individual degrees of freedom? All right, thanks for your attention.